All right, fusion reactions. This is when a small nuclei fuse together to make a larger one. These reactions naturally occur in the sun. So in the sun, we know that it's made up of mostly hydrogen and helium. This is because hydrogen, being the fuel, is slowly turning into helium through this process. It's actually a little bit more complex than this, but in this case, we're just talking about one possible fusion that happens in the sun. Deuterium is actually just hydrogen 2, if you remember the terminology, and tritium is hydrogen 3. So you may see these again, but in most cases, I'll probably remind you what those are. So if hydrogen 2 plus hydrogen 3 form together at high speeds, high temperatures in a collision, and as a product, we see that has a daughter nucleus of a helium, and also must produce one neutron in order to balance out the number of nucleons and, of course, the number of charge. So the advantage of this is abundant fuel. Hydrogen's all around us. We do get stable byproducts. So the byproducts here is helium. So once again, if we were to somehow be able to create this here on Earth, we would just have a whole bunch of helium left over. And of course, helium is something that we can use to fill up balloons and other things like that. Disadvantages, I mentioned that it has to be high speeds or temperatures. It's usually high pressure as well. So in this case here, it says high temperatures, roughly 1 times 10 to the 8 Kelvin is required to overcome the repulsion of the nuclei. Once again, hydrogens are mostly protons and neutrons. And how do we get protons to form with other protons? Well, it has to be in these conditions of extremely high temperatures, high speeds, or high pressure in order to do this. All right, so there's this graph that you'll see. This one here is all about trying to become more stable. In the beginning here, we'll see the number of nucleons, and we'll see that hydrogen with another hydrogen form to make helium. And in this process, it is jumping up. So if a hydrogen plus a hydrogen forms helium, once again, this is just one example. I'm not putting all the numbers here, just a very quick example, but it will jump up. And it will jump up because in this case, helium has more binding energy per nucleons. So in other words, more binding energy means it's stable. So the higher this thing is on this graph, the more stable it is. So if you take a look at which one is the highest, usually we're talking about iron in this case. Iron is a very stable element. So uranium will break into 2 smaller things. When it breaks into 2 smaller things, those products will have a higher binding energy per nucleon. Once again, to become more stable. The higher the binding energy, the more stable the atom is. So you need to know this graph, what it looks like, what side is fission, what side is fusion, and that's pretty much it for this graph. All right, here's a nice equation we can try out. So example, determine the energy release when uranium-235 with a mass of 235.044 atomic mass units absorbs 1 neutron, 1.009 atomic mass units, and produces barium-141 and krypton and neutrons. Determine the energy release. The energy release. So what we need to do for these types of questions is find out the energy before, compared it to the energy after. If there's a difference, we can then use that binding energy equation, or the energy for a change in mass, to then solve out how much energy is released through this process. So kind of like how we did with the element where we found out the number of neutrons and protons, except for this case, we're not going to break it down to neutrons and protons. We're just going to use the mass of the nucleus, in order to kind of solve this one through. So let's take a look at our equation first. Let's write it out just to make sure we can figure out. And neutrons, well, how many, right? How many neutrons are there? So I'm going to say 235, 92. A neutron, so plus 10 neutron. Barium, 141. Barium is, find it on my sheet here, 56. And krypton, 92. And krypton is Kr, and Kr is 36. I'm trying to look at my sheet and it's sideways and it's wrecking my eyes here. Plus something, right? So we need to figure out how many neutrons there is. So I'm guessing it's 3 because this is the one we've done earlier, but let's double check. 235 plus 1 gives us 236 minus 141 minus 92 gives us 3. So yes, we have 3, and then down below we have a 0, so this must be 3 of the neutrons. All right, so I want to find the mass of this. What is the mass here, and then what is the mass here? So mass, let's say before, mass after, and then I want to find the change in mass. Okay, in this case we should have lesser mass after. So I'm actually going to say mass before minus mass after. From this mass, I then want to convert it once again to kilograms, and then I want to find the energy by using the delta M c squared. And we could convert it into mega electron volts if need be. All right, so I'm just going to keep all the numbers first off in atomic mass units, then find the change in mass, then convert it to kilograms instead of converting each of them into kilograms. So 235.044 plus 1.009 gives me 200, oops, that's not a 2, 236.053. And I'm going to keep as many sigdigs as my calculator gives me. 140 plus 140.914 plus 91.926 plus 3 times 1.009. So make sure you multiply this by 3. And the mass after gives me 235.867 U's. Once again, I mentioned that before is going to have more than after, which is good. So therefore, we're going to find the change in. So first number minus my second number gives me a difference of 0.186 U's. I want to convert this into kilograms. I can do that by multiplying by 1.66 times 10 to the negative 27. So remember, that's 1.66. Okay, and I end up getting 3.0876 times 10 to the negative 28. And that is in kilograms. So using Einstein's equation, multiply that by the speed of light squared. So times 3 times 10 to the 8th squared gives me 2.778884 times 10 to the negative 11 joules. For this case, if I wanted to solve out for the mega electron volts, I would then divide it by 1.6 to the negative 19, and I would get 173 let's just go 0.7 mega electron volts. So this is one way that you'll see an answer written down in mega electron volts. Technically, the joule one would be correct, depending on the question. In most cases, they'll ask for it in mega electron volts or in joules. Another thing that you could see is saying, what is the energy release per nucleon? And remember, nucleons, well, if you take a look here, there's 236 nucleons. And there's 236 on the other side. So sometimes you'll see it say per nucleon. Once again, depending on the question. But in that case, you would take your energy and divide it by 236. So if I divide that by 236, I end up getting 0.736 mega electron volts per nucleon. Once again, depending on the question, you might be able to choose option A, option B, or option C, depending on how the question's worded. All right, so try these questions out. It's all about balancing nucleons, balancing charge. Try some of these harder questions, which is talking about energy released. Once again, comparing the mass before and the mass after, and there should be a change in mass, and that change in mass can be used to determine the energy using Einstein's equation. All right, so try the rest of the questions. Next week, you'll see that we are going to be doing half-life, and then we're also going to be doing other particles, and that's going to be our last lesson is going to be next week. So after that, we will have maybe a review followed by our unit exam. All right, so prepare for that. Okay, take care, guys.